Hello, my name is Dan Brunner, and in this video, I'll be going over how to solve problem 6.020 from Chapter 6 in the Fundamentals of Mass and Heat Transfer textbook. So looking at the problem statement, we're considering a laminar boundary layer that's developing over an isothermal flat plate. We're going to assume that the flow is incompressible and that the viscous dissipation is negligible. For part A, we'll be essentially turning dimensionless forms of the thermal boundary layer boundary conditions into their dimensional forms. For part B, we'll be doing something similar, and we'll be transforming the dimensionless form of a conservation equation into its corresponding dimensional form. So for this problem, the assumptions were pretty much given to us in the problem statement. We're assuming that we have laminar flow. The flat plate that the fluid is flowing over is isothermal, meaning that the temperature is the same anywhere on that plate surface. The flow is incompressible and there is negligible viscous dissipation. That last assumption will be important for part B. So we're given many equations for this problem, and we have to substitute some into others and simplify down. All of these equations are given in chapter 6 of the textbook. So the first equation that we're given is an energy conservation equation for the fluid that's flowing over the flat plate. Whenever you're analyzing the fluid flow, you have to make sure that energy and mass are conserved. So this is your energy conservation equation. We're also given the dimensionless forms of our independent variables, x and y. The and Equation 6.32 and 6.33 show the dimensionless forms of our dependent variables, including the velocity components in the x and y directions, as well as our dimensionless temperature. All of the dimensionless variables are denoted with a little star. The equation 6.36 is the dimensionless form of equation 6.29. And equation 6.39 shows the dimensionless forms of the boundary conditions, which will be important for part A. We're also given the Reynolds and Prandtl numbers for those corresponding equations, and those will be important for part B. So looking at part A, we have equation 6.39, and when we substitute equation 6.33 into that equation and simplify, we get that the first boundary condition is just the temperature at a given x coordinate, and at y equals 0 is equal to the surface temperature of the plate. For the second boundary condition, we can simplify in a similar fashion, bring the denominator over to the other side, and then isolate this temperature function. And we get that the temperature is equal to the ambient temperature at y equals infinity and any x. For part B, we have equation 6.36, and when we substitute in equations 6.32 and 6.33, we can arrive at this equation right here. And to simplify these differentials, you can, assume, that the denominators in both the numerator and denominator differential terms are constants. And so you can just take those out front. So in the next line, you can see that if I take out this 1 over L, dividing by 1 over L brings this L up into the numerator. And you can do something very similar with the temperature difference between the ambient and the surface temperature. And so when you do all that and go through some other simplifications, you can arrive at equation 6.29. As you can see, this is exactly the same, except it's missing the viscous dissipation term, that's in 6.29, because we assumed that was negligible. So that is how you solve problem 6.020 from chapter 6 in the Fundamentals of Mass and Heat Transfer textbook. Thank you.